Now, let us talk about the centroid of bodies in 3 dimensions. So it is pretty clear that in 2 dimensions we were able to find the centroid of a body by combining and adding the areas of regular objects. When we didn't have a regular object, we would have to compute the integral of the functions in 3D, which that could be complicated. But in 3D is the same case. If a body has a regular geometry, let's say for instance a cube, the centroid is located with respect to the coordinate system. Okay? That is something that we know by now. Okay, there, let's assume the coordinate system is right at the edge. So we're gonna have x. Actually, we can even make it simpler. So we have positive coordinate system. So we say this is x. We have y at that place going up and z coming towards us. In that case, the center of the centroid of the geometry is going to be having coordinates in x, y, and z. That is clear. And it's going to be somewhere around here. Alright, so that will have coordinates in x, y, and z. That is the center of gravity. Why is so important? Well, it's important because then we can have the force or the weight of that body applied to that center or centroid. And then we can have moments with respect to any point or axis that we want. So the concept is that if we have a body with a with a center of gravity or a centroid, first of all, remember that if it's going down but the positive axis is going up, that force has a negative component in the axis. So if this axis is x, it's going to be negative j. If they give us another situation where a second axis where, let's say, this is x, this is y, and this is z, which is pretty common in many coordinate system and many software. In that case, this is negative force, but the component in k. So be careful which coordinate system they're giving you, because then the force component will be either in y, in x, or in z. And it could be positive or negative depending where your axis is pointing. In this case, y is vertically is going up, so the force is negative because it's going down. We located the centroid, the center of gravity. And in a case where we have many regular shapes, so we're going to do a summation of volumes. Say this is a shape, and this is another shape. And you can even have a third shape. Okay, in that case, you do the summation of the volumes. So the centroid in x, as before, is going to be the coordinate. Well, it's going to be a function of your x. Centroid in y is going to be a function of y. Centroid in z is going to be a function of z. So now we're talking about volumes. And in that case, you must know what is the distance r, the radius, not the radius, but the vector from the origin to the point. Because if you have x, y, and z, r will have coordinates in I, j, and k. And you can even have the magnitude of r by doing square root of each component. So in that case, it's simpler to create or find the centroid of of the whole body, and then find a single r of single vector that will take you there, so that we can find our main force. Remember how before we had an example where even though we were computing the area, that region was really a force? Same here, the volume will represent the amount of force of the body. So that's why we're talking about W. And W is the summation of all the objects that we have and discrete objects that we have. Okay? And that's the same case for a vectorial representation of the x, y, and z times w is this case, because this will give you the component in I, in j, and k. Alright, so let's look at an example. Well, first, sorry, before the example, we have to, there's pretty important table that will give us what most of the geometries that we can use for regular shapes. So this concept right here is for the volume and the centroid of regular objects. Hemisphere. So this is half of a sphere. All right, and the volume, in case this is too small, I'm going to write it down here, is 2/3 of pi and r in cubic r, so radius to the third power. That is the volume. Now the centroid, so be careful because the radius is with respect to the base. Okay, that's the radius A. The centroid is with respect to the base as well. So I don't know if I'm going to be able to draw this nicer, but say, and the thing is that it's in x, y, and z coordinates. It's not in polar or cylindrical coordinates, which a lot of times is easier for spherical shapes, or even spherical coordinates, that's a thing too. We haven't talked about that, but spherical coordinates are used for this type of thing. But in Cartesian coordinates, you have a base, and then you have your surface around that half surface or half sphere. And this closed set of surfaces, the base and the half surface combined, will give you a volume. All right, so in this case, the centroid is with respect to y. In this case, respect to x. So be very careful when you find the centroid is with respect to the axis that they're asking you, that you have specified. And in this case is 3 times the radius over 8. 3 times the radius over 8. That is the centroid. Okay, let's do the next one. This is half of ellipse. So the volume for half of ellipse is equal to 2/3 of pi times radius squared times h. And h is the long axis of the sphere. The centroid, here's x, in a case like this would be y, is equal to 3h over, depending on the axis. I don't want to confuse you like that, so let's do this. If it's this axis, in a case like this, x, y, and z, x, y. In this case, the centroid along x is 3 times the height divided by 8. That will give you the point in x. So it's along the x-axis. If you have this flipped, rotated, and is towards y, then it will be y, centroid along y. All right, this is a parabolic. Well, this is a parabolic revolution. So if you have a parabola, and for those of you who took CAD or AutoCAD, you know that if you revolve the surface and then create a volume, then you have a 3D solid body. In this case, the volume of of a parabola, a revolved parabola, is 1/2 of pi radius squared times h. So it's similar to half ellipse, except for instead of 2/3 is 1/2. And the centroid along x is height over 3. All right, we have a few more objects. The cone is, again, along x. And also, careful with another thing. If the cone is up, it's a mirror basically. If the cone starts here and the base is over here, then it's going to be h minus the centroid. For instance, if the shape they gave you was a base, I don't know if I'm going to be able to draw it nicely, but well, let's do something else, because I don't know if I'm going to be able to not draw it as nice. If the coordinate system was applied here, x, y, z, and if you didn't want to move, you can move the coordinate system. Just be careful when you move the coordinate system that everything else is referenced to the coordinate system. If it's, for instance, there, then your centroid, remember the centroid is with respect to the base. So the centroid would be, okay, what is my base? The base, if this is r, there, so a is the radius, minus 3, 8, or 3a radius over 8. This will be this distance. Same here, this distance, if the coordinate system was here, would be h, because now is going back to the base minus 3h over 8. And actually, this is going to give you, so be careful, because if this is this 0, this is going to be towards the left. So you might need to do a negative here and a negative here. So it's really depending on where you do your coordinate system. Okay, so I don't want to have all this in the notes because I don't want to confuse you once you open the notes by yourself. But just to make sure that you know where your base reference is. In this case, we're referencing just that centroid. This is the number 3a over 8 because our 0 starts here. If they're asking you for this length, is basically, that's what I'm getting at. That between this centroid and this end is a minus 3a over 8. This length is h minus 3h over 8. And so on and so forth. So you get the concept. This distance right here is h minus h over 3. So 2h over 3. This is this distance right here up to this point. And so on and so forth. All right, so the other shapes that we have are the cone and the pyramid. So the cone has a volume of 1/3 pi, the radius of the base, squared times height. So it's just like a cylinder, except for you multiply it times 1/3. And the height from the base is h over 4, height over 4. And of course, if we do the same concept here, the height, the centroid from the tallest point is h minus h over 4. Okay, we have one more, which is the pyramid. The pyramid is volume equals 1/3 of A times B times H. And A and B are the base of the rectangular shape. If it's a square, it's just A squared. If it's a rectangular pyramid, it's A times B times H, and times 1/3, otherwise it will be a cube. And the centroid is at h over 4 with respect to the base. Again, with respect to the tip of the pyramid, it will be h minus h over 4. All right, so with that, let's do this example.